Hello. So now we are going to look at the Maxwell's equations, which form the basis of all electromagnetic interaction. These are four equations that govern the sources, which are charges and currents, and the corresponding fields, which are electric and magnetic fields. A self-consistent description of all this is what comprises the Maxwell's equations. Its applicability is from small scale all the way from 10 power minus 15 to astronomical scales. So it's one of the most successful theories that we have ever come up with. The question I'm going to address now is why Maxwell's equations are so successful. So the success of Maxwell's equations relies on the fact that there is parametrization of the medium, and that is an essential feature that makes it applicable to a variety of problems. So the sources for us are charges and currents, and the fields are the electric and the magnetic fields. Now, what I want to discuss first is this notion of microscopic versus macroscopic Maxwell's equations. So let's look at an elementary collection of charges, which could be an atom. So you have a set of electrons, you have the nucleus, and you see the classical model of atom is this electrons whirling around the nucleus, and you would realize that the fields are extremely large as you come close to a charge, and they get smaller and smaller as you go away. So you would see that in such a dynamic system, which is localized to a scale of about angstrom, you're going to see a lot of discontinuities in the fields because charges are dynamically moving around, they're whirling past each other, and it would be extremely difficult, if not impossible, to solve this dynamically because the change is happening so quickly and at such scale that to get a hold of the electric and magnetic field at this microscopic scale would be extremely challenging. The other relevant scale that we have is that of measurement. So whenever we measure something, we are not actually tracking the intercharge field within the atom. What you are looking at is a probe which sort of averages over a large piece of the sample, not just in space, but it also does that in time. That is, I have got a detector that detects, for example, an electric field, and there is a response time of the detector. That would mean until the detector accumulates that much information, there is no reading on the detector, and hence there is an averaging process which is inbuilt in any detector, which is governed by the response time of the detector, right? So measurements are macroscopic, but how macroscopic is it? So what we do is, when we talk about a macroscopic measurement, we always average over a microscopically large volume. That is, I'm not looking at individual electrons or nuclei, but macroscopically small volume. So I'm not looking at the whole collection as a single object, but I'm looking at this intermediate scale where I have collection of or maybe 1,000,000 atoms, yet this scale is smaller than the bulk scale of the problem, right? It is this nuance that we need to understand. Let me just give you some numbers. So for example, if you look at the discontinuities which I talked about, these are in the angstrom scale, right? There's 10 power of 10 meter. This is the level of electrons, protons, and the coupling neutrons and so on and so forth. This is that scale we are talking about. The second scale is that of your probe or your detection. Let's keep our context to optical. If I'm making an optical measurement, then I have lambda is my spatial size, which is relevant, right? And for optical, that is about 500 nanometers. So the point about a spatial scale is that, so the probe is not going to be sensitive to structures which are smaller than the wavelength of the probe itself. On the other hand, we have a notion of a time scale. So if you look at time, then it is essentially given by, the inverse of the frequency. This, as you know, is 10 to the power of minus 14 seconds. This is the time scale that we do not resolve in our measurements. So what we do, the time scale essentially is governed by the response time of the detector. Response time could vary from, let's say, milliseconds, right? It could be in microseconds, or it could be in nanoseconds. The moment you come up with, let's say, a nanosecond response, right, you are already averaging over about 10 to the power of 5 cycles, right? So this is how one is not really looking at the variation of the electric field at that scale, but one is looking at an averaged quantity. So once you're doing this, we have got these various scales. There is an intrinsic inbuilt scale. There is a macroscopic scale of measurement. The question one asks is, does one really require the detail of the microscopic scale, or can one do without it? And that is where this transition between microscopic and macroscopic happens. So let me show you the way it is implemented. So for example, I take my sample, right? This is a bulk sample. And what you have is basically variety of charges and currents which are flowing around in such a material. And you would see that at any point in space at this scale, the electric and magnetic fields are dramatically changing at this small scale. So what one considers is a volume, right? So let me use another color. What one considers is a small volume. Now, in this small volume, what I do is basically measure across this whole volume. What one does is to consider the field within this volume, right? And take a average. So imagine I have taken the field at 100 points within this. I'm looking at the total field divided by 100. Then to get the field nearby, what one does is, so for example, this is the field I would associate with this point at there. Now, if I want a field which is near to that, so what I do is consider another volume which is centered around the green point now, right? And this is a volume you would clearly see. For the most of it, it contains all the points in the previous volume, the red volume, yet it has left out a little bit, right? And it has taken some extra volume. So you can clearly see that the averages between these 2 points are not going to differ dramatically, because the bulk of it, even though they are fluctuating fields, they are going to more or less more or less vary only smoothly across this variation of the across this spatial variation. And so one can estimate, for example, let's say I am looking at a scale of hundreds of nanometers, right? So this is 10 to the power minus 7 meters, whereas the spacing between atoms is about 10 to the power minus 9. So even if I look at a wavelength size averaging or a volume which is wavelength size, you will see that I'll quickly get essentially, 10 to the power of 2 cube number of atoms within such a scale. So this is my interatomic distance in 3 dimension is going to give me, about 1 million atoms. So you see clearly I can, so for a probe with optical wavelength, I am clearly averaging these electric and magnetic fields over a million atoms. The effect of this is that my E and B fields, mathematically, they become analytical functions. They are smoothly varying analytical functions. So where on one hand you had extremely randomly uh, varying fields, but because of this notion of averaging, what one is getting is basically fields which are nicely smoothly varying functions of space and time. So okay, so now that we agree on this, let us just write down the Maxwell's equations. So before I get to Maxwell's equations, I want to indicate a few things. I want to basically make sure that we know the two integral theorems. I want to write down the Maxwell's equations both in the integral form, that is what you would have learned in your school, and physically interpreted it, and I also wanted to write it in the differential form. To go from these two forms, we require essentially two theorems, which I'll briefly state. One is called the Gauss's divergence theorem, and the other one is the Stokes theorem. Gauss's divergence theorem states the following. Let me consider a vector field. By vector field, what I mean is that every point in space, I have got a vector, and this collection globally taken together forms basically a vector field. So what it deals with is the following. So imagine the vector field it has got some structure in space. What I do is basically consider a volume. We are looking at the field within such a closed volume. So this volume is characterized by its volume itself, and it is also characterized by a surface, okay, surface that encloses this volume. So these are the two things that we will characterize this enclosed region with: its volume and the surface that encloses it. So the Gauss's theorem simply states the following. If you look at the net outflow of the field, that is, you look at F dot dA on this closed surface, let me call this the same area A, and such a quantity. What is this quantity? So if you look at it closely, so let me focus myself on a particular area element. So let us say that this is the normal at that surface of that area element whose normal I have drawn, and you can clearly see that my field at that point might have a direction which is different from that. So all that I need to do is I need to do F dot dA. I need to do this across the whole surface that is enclosing it, and the Gauss's divergence theorem states the following, that F dot dA is basically the volume integral, that is, in the volume of it, if I calculate the divergence of this vector field, right, and integrate it over that volume, then these two quantities are equal. Remember that this V is precisely the volume contained within that closed surface A. So I'm indicating the closed surface by this circle over the integral. I hope this is clear. I'm not going to look at the proof of this, but we are going to utilize this to go from the integral form of the Maxwell's equation to the differential form. Similarly, one talks about the Stokes theorem. So again, what I have is, again, I have the vector field F. And what I'm now doing is basically looking at the following. I have got a loop within this vector field. Remember that the field is everywhere. So I'm considering a loop. I'm indicating that closed path with the letter C. This closed path itself can support, for example, a surface. So imagine I consider a surface S, right? This surface is such that it is an open surface in the sense that it doesn't contain within it a volume. The only requirement for this surface is that the surface boundaries match with this closed path, the loop C, right? And you can clearly see that the surfaces are not necessarily unique. For example, I could have drawn another surface whose boundary is exactly the same. So I could have drawn a surface like that, right? In such a way that its boundary is precisely the original loop C. So this could be another surface which also has the same boundary. So the surface in this situation is not unique, and usually it is taken depending on the symmetry of the problem. One can play around with the surface. The Stokes theorem statement is the following: that if I look at the total circulation of the field around the loop, what do you mean by circulation? You take F, you dot it with dl, which is the line element along the loop, and then you integrate it over the closed loop, and then you would get the following: integral over the curl of the field, this is a vector quantity, and you dot it with dA, which is the for example the area element. So let me quickly indicate what we have here. So for example, so dl is that way. F I have already indicated, so you're looking at f dot dl, and then you are looking at these dl as dl keeps changing as you go around the closed loop, and that is on the left hand side. On the right hand side, what you have, for example, is let's say area element. In that situation, you have dA, which is on that surface. You are calculating the del cross F, right, at this surface, and then you are dotting it with dA. So that is the kind of notion that you have. And remember that this surface can be any surface, such a way that its boundary is unique. Surface can be varied. Okay. Again, this is not a closed surface, and hence I have not put the circle in my integral. This is an open surface. All right. So now that we have these two theorems, we will use them essentially to get to the integral and differential forms of the Maxwell's equations. So let me write down the Maxwell's equations. So I will first write down on the left in the integral form, and from there we will just implement these two theorems and get to the differential form. Right. So the first one is the Gauss's law, which is, so if I look at the net outflow of the electric field, right, just in the previous case, E dot dA over a surface A, and this is equal to, so the net outflow is related to the total charge, volume charge, which charge density is given by rho, and this the integrate over the volume, and you divide this by epsilon naught, right? So this is a statement of the Gauss's law, which tells you that the net outflux of the electric field is dependent on the net charge within an enclosed volume. So this is Gauss's law. The second equation is that which relates again to the net outflow of a magnetic field, and the statement is this, that the net outflow of magnetic field through any closed surface is always going to be zero. There are no notions of magnetic monopoles. This statement essentially stating that there are no sources and sinks for the magnetic field. So the third Maxwell's equation is the Faraday's law, which tells you that if I am looking at the EMF or E dot dl, which is the force per unit charge across a closed path C, this arises because of a time dependent change in the magnetic flux, which is B dot dA. Now this surface S is the open surface whose boundary is what we are talking about here. The negative sign here is the Lenz's law, right? And this is the Faraday's law. So the time rate of change of the magnetic flux actually produces this EMF. The fourth equation is the Ampere's law, which essentially states the following, that if I'm looking at the total circulation of a magnetic field about a closed loop, then that is equal to mu naught times, so there are two currents, the current which is J, which is current density, plus a change in the electric field. This is the Maxwell's correction to the Ampere's law. The change in the electric field itself acts like a current, and dotted with dA, which is the area enclosing that particular loop C. Right? So this is the Ampere's law, and this particular object is the Maxwell's correction that you already know of. So now let's quickly write these down in the differential form. So in the differential form, what I have is, remember that the closed surface integral E dot dA can be replaced by a divergence of E, right, dot dV, and now you look at only the corresponding integrants, so that what you get is essentially something like this. On the right hand side you have rho, which is the charge density, and on the left you have this. Similarly, the second integral goes to del dot B equal to 0. The third integral, again, remember that on the left hand side your E dot dl is essentially open surface integral of a curl, so that gives me curl of E being equal to minus dou by dou t of the magnetic field. Again, we are looked at only the integrants, and we find that both the integrals are of the same kind. Please implement this for yourself and convince yourself that this is indeed true. And similarly, we have the Ampere's law, which is del cross B is simply mu naught J plus epsilon naught mu naught dou E by dou T. We have written all these equations in the SI units. That is why you see this epsilon naught and mu naught. Remember, epsilon naught is the permittivity of electric permittivity of free space, vacuum, and mu naught is the magnetic permeability, again of vacuum. Right. So these set of equations is what I am calling these as microscopic Maxwell's equation. They are microscopic because what you are keeping track is basically the actual distribution of charges. These are the sources, right, and the currents, and then you are looking at these electric fields, which depending on the location of these charges and current, which could be of at the microscopic scale, would give you the corresponding electric and magnetic fields. So now let us make a transition from this microscopic to a macroscopic description.